KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to discuss the next continuation example problems, example 11.6 and then example 11.7. Right, first you see the example 11.6. What is the temperature of the steel copper junction? What is the temperature of the steel copper junction in the steady state of the system shown in the figure? So this is the figure you can see. This is what furnace at 300 degrees centigrade and ice box at 0 degrees centigrade, and it is the steel and it is the copper, right? And here insulating material. So there is no chance for the heat energy to flow from here to surroundings and from surroundings to there also. From surroundings to there also. Okay, right. So this is the picture or this is the system what we have seen in this picture or figure. But here finally what he is saying means, and I mean basically what he is saying is, it is the steel copper junction which is in the steady state. It is the steel copper junction which is in the steady state. Okay, that is. Now, length of the steel rod is equal to 15 centimeters. Length of the steel rod is equal to 15 centimeters. Length of the copper rod is 10 centimeters. Temperature of the furnace is equal to 300 degrees centigrade. Temperature of the furnace is equal to 300 degree centigrade, right? That is one thing. And after completion of that, if you see, they have given some other values like a temperature of other end, that is what 0 degree centigrade, right? So temperature of the furnace 300 degree centigrade, temperature of the other end, that is ice box at 0 degree centigrade, length of the steel rod 15 centimeters, length of the copper rod 10 centimeters. Okay, that is. Now see, based on the given data, not only the given data, what is there in the problem, they have given some other, that is thermal conductivity of steel. So in our previous classes we discussed, in our previous class, there was one table. So in the table we had the values of thermal conductivity for steel and copper, right? So for steel, how much is it? For steel it is 50.2 joule per second per meter per Kelvin. Similarly, for copper it is 385 joule per second per meter per Kelvin. Okay, right. So these are the values which are like constant values. No, we know how to determine the thermal conductivity for one particular material, but after determination you can treat it as a constant value when we are going to solve the problem. Right. In this problem there is a junction which is a steel copper junction in the steady state. After that, the length of the steel rod is 15 centimeters, length of the copper rod is 10 centimeters. Temperature of the furnace is 300 degrees centigrade. Temperature of the other end is 0 degree centigrade. Temperature of the other end is 0 degree centigrade. Okay, that is. Next, the area of cross section of the steel rod is twice that of the copper rod. The area of cross section of the steel rod is twice that of the copper rod. That is also one more important point which we have to use to solve the problem as given. Okay, And here finally we have to find out the temperature of the steel copper junction. Temperature of the steel copper junction, right? See here. First we have to write the given data. Okay, this is what the picture, and the given data means we already know, no? That is length of the steel rod and length of the copper rod and temperature of the furnace and temperature of the other end, and thermal conductivity of steel and thermal conductivity of copper. And one more point, that is area of cross section of the steel rod is twice that of the copper rod. Even in the picture also you can see, but exactly he is saying which is twice. Now see, the insulating material around the rods reduces heat loss from the sides of the rods. It is the quite thing, no? Quite normal thing, no? See, there is no conduction from here to somewhere. I mean, from here to surroundings and from surroundings to here also, right? That is. So here, because that's why he mentioned clearly insulating material. Okay, that is. So regarding this insulating material, there is no flow of heat from here to surroundings and surroundings to here. The insulating material around the rods, reduces heat loss from the sides of the rods. That is one thing. Therefore, heat flows only along the length of the rods. So whatever the heat which comes from here to there, which is going to flow, it flows only along the rod. That is what steel copper junction rod. Okay, it is what you can call it as steel copper junction, but it is copper rod, it is steel rod. So heat flows from here to there or from there to, okay, right, it is generally from a body at high temperature to the body at low temperature. So what can we say? Heat flows only along the length of the rods. Now, consider any cross section of the rod. Now, in the steady state, already he mentioned in the question, that is what in the steady state. In the steady state, heat flowing into the element must equal the heat flowing out of it. In the steady state, heat flowing into the element must equal to the heat flowing out of it. Otherwise, there would be a net gain. Otherwise, suppose if it is not happening, what is not happening? Suppose if heat flowing into the element must not equal to the heat flowing out of it, means there would be a net gain or loss of heat by the element, and its temperature would not be steady. But in the problem, clearly he mentioned here, in the steady state, that's why you can consider and you can say confidently, heat flowing into the element must equal the heat flowing out of it. Okay, right. Now see here, in the steady state, rate of flow of heat flowing across a junction. In the steady state, rate of flow of heat flowing across a junction of the rod is the same at every point. Along the length of the combined steel copper rod. Okay, right. Now, let T be the temperature of the steel copper junction in the steady state. For example, if capital T be the temperature of the steel copper junction in the steady state, we have to find out T, no? That only he is asking, no? What is the temperature of the steel copper junction? So that temperature now we assumed, we are taking as English letter to represent temperature. That is what already we came to know. That is capital T. So let capital T be the temperature of the steel junction in the steady state. Then what can we write? See the step. K1 into A1 into 300 minus T divided by L1. See how we are writing this one regarding that means, in our previous class we discussed, that is what H is equal to Ka into Tc minus Td by L. Right? So from there, here we are writing K1 into A1 into 300 minus T divided by L1 is equal to K2 into A2 into T minus 0 divided by L2. Now we are going to substitute the values because K1 is the thermal conductivity of steel. That is what given ma. Otherwise you can feel like a constant value because constant values always will be given, no? Right. So here also they have given, but I am saying K1 is 50.2 into, he mentioned here, see the area of cross section of the steel rod is twice that of the copper rod. That's why here he kept 2. Here it is like it is A1 and it is A2. So it is for what? Steel. So steel is twice that of this, no? So in place of A1 you can write 2A2. A2 will get cancelled mathematically, and finally here we are getting 2 into 300 minus T divided by L1. L1 is 15. L1 is 15 given, that is 15 centimeters. So you can take it as directly because cancellation will be there, no? This side also we have equation, this side also we have equation. That's why we no need to bother about the units. 15 centimeters is equal to, here K2 is 385, no? That is thermal conductivity of copper, 385. And A2 I already told you how, why the area of cross section will give 2 here. And T is T minus 0 means T will come divided by 10. Divided by 10. So after completion of this, what is the T value we are going to get? That is 44.4 degrees centigrade. 44.4 degree centigrade. By solving this equation, we will get T value as 44.4 degrees centigrade. And here 1 and 2 refers. See, because here we have mentioned 1, here we have mentioned 2. See, what is 1 and 2 refers, na? Steel and copper rod, no? Steel and copper rod. And I already told you A1 is equal to A2 according to the question. And then L1 is equal to 15 centimeters given. L2 is 10 centimeters given. K1 value also given 50.2. And the K2 value also given like 385. Steel has 50.2 joule per second per meter per Kelvin, thermal conductivity of steel. And then for copper, thermal conductivity is 385 joule per second per meter per Kelvin. Right. So finally we got the temperature of the steel copper junction in the steady state is 44.4 degrees centigrade. 44.4 degrees centigrade. Now we are going to see the next continuation problem. Example 11.7. An iron bar and a brass bar. They have given measurements, but I didn't write, but I am saying while substituting again, because here we have written clearly. See, in the given data I have written, but here I didn't write. See, an iron bar and a brass bar. An iron bar and a brass bar. For iron bar, length is 0.1 meter. L2 is equal to L1 is equal to L is equal to 0.1 meter, right? And area of cross section for iron bar is 0.02 meter square. And thermal conductivity is 79 watt per meter per Kelvin. And a brass bar, L2 is 0.1 meter, A2 is 0.02 meter square, and K2 is 109 watt per meter per Kelvin. Okay, that is. So for iron bar and brass bar, these are the measurements they have given. An iron bar and a brass bar are soldered, soldering, soldering in TV shops and radio shops they used soldering gun, right? So these two bars soldered end to end as shown in the figure. See this picture. The free ends of the iron bar and brass bar. So it is the free end of the iron rod, it is the free end of the brass bar. The free ends of the iron rod and the free ends of the iron bar and brass bar are maintained at 373 Kelvin and 273 Kelvin respectively. So this is the given data. What is the given data? The length of the iron bar and length of the iron bar and area of cross section of the iron bar, and length of the brass bar and area of cross section of the brass bar, and then the temperatures at these 2 points. That is what the free end of the iron bar at 373 Kelvin and the free end of the brass bar is 273 Kelvin. And they also given the thermal conductivity of iron, that is 79 watt per meter per Kelvin, and the thermal conductivity of brass, that is 109 watt per meter per Kelvin. Based on this given data, he is asking to compute first the temperature of the junction of the two bonds, right? Next, second one, the equivalent thermal conductivity of the compound bar. Very good, very interesting question here, because we are going to calculate the equivalent thermal conductivity. Still now, in our previous class, we came to know only the thermal conductivity of different materials like iron, silver, copper, water, oxygen, like that. Now we are going to calculate the thermal conductivity of the compound bar. And third one is the heat current through the compound bar. The heat current through the compound bar. That is the third one we are going to compute. So here we have to compute or calculate three things. One is the temperature of the junction of the two bars. First we are going to discuss that one. Then we will come to discuss second, and then finally third one. But before going to discuss this first, second, third, first we have to get the resultant thermal conductivity or equivalent thermal conductivity. See here, step by step. Please be observed carefully. See, this is the given data. So you can write. Under the steady condition, H is equal to H1 is equal to H2. Is it the statement we can write now? Once you think. Because in our previous problem also we used the same scenario, same situation. Under the steady condition, H is equal to H1 is equal to H2. When H is equal to H1 is equal to H2, you can write the next statement. That is what K1 A1 into T1 minus T0 T0 divided by L1 is equal to K2 A2 into T0 minus T2. T0 minus T2 divided by L2. Okay. For A1 is equal to A2 is equal to A, and L1 is equal to L2 is equal to L. You just assume. See, what is A1 is equal to A2 is equal to A? The area of cross section of the iron bar is equal to area of cross section of the brass bar. Similarly, what is L1 is equal to L2 is equal to L? Length of the iron bar is equal to length of the brass bar. So, if you substitute these two things here, what will happen? This is the final. From this equation, we are getting this one. K1 into T1 minus T0. K1 into T1 minus T0 is equal to K2 into T0 minus T2. See, when you are writing L1 is equal to L2 is equal to L, this will be get cancelled, no? Because of right hand side term and left hand side term. When you are writing A1 is equal to A2 is equal to A means this will get cancelled, no? This one and this one will get cancelled, no? So what is the final thing? K1 into T1 T0 is equal to K2 into T0 minus T2. Now, does the junction temperature T0, see, we assumed junction temperature as a T0. Thus the junction temperature T0 of the two bars is T0 is equal to K1 T1 plus K2 T2. K1 T1 plus K2 T2 divided by K1 plus K2. Thus the junction temperature T0. Thus the junction temperature T0 of the two bars is T0 is equal to K1 T1 plus K2 T2 divided by K1 plus K2. K1 plus K2. Now, using this, the heat current through either of the bar, either iron bar or brass bar. Using this, that is what T0 is equal to K1 T1 plus K2 T2 divided by K1 plus K2. Using this equation, the heat current H through either of the bar, H is equal to K1A into T1 minus T0. See here, K1A into T1 minus T0 divided by L. That is equal to K2A into T0 minus T2 by L. See, in place of this, we are going to use this equation. In place of T0, we are going to substitute this value. From that, mathematical treatment of these two equations or of these two relations will give us K1 K2 by K1 plus K2 into A into T1 minus T0 by L. So, just in place of K1 only we are writing this is what. But after completion of that, see, this is the same. You can see is equal to here also A into T1 minus T2, A into T1 minus T2 divided by L into 1 by K1 plus 1 by K2, 1 by K1 plus 1 by K2. Using these equations, the heat current H dash through the compound bore. Using these equations, the heat current H dash through the compound bore. Compound bore means what? The combination of iron plus brass. Iron plus brass. So the current H dash, heat current H dash through the compound bore of length L1 plus L2 is equal to L, because here we assumed L1 is equal to L2 is equal to L, no. So then L1 plus L2 means what? L plus L, which is equal to 2L. And the equivalent thermal conductivity, K dash of the compound bore are given by H dash is equal to K dash into A into T1 minus T2 divided by 2L. That is equal to capital H. So where K is equal to 2K1 K2 by K1 plus K2. This is the equivalent thermal conductivity. 2K1 K2 by K1 plus K2. Okay, right. Now, first one. T0 is equal to K1 T1 plus K2 T2 by K1 plus K2. See, we have to substitute. See, I already told you what is the thermal conductivity of iron and what is the thermal conductivity of brass. Here also you can see what is the value of K1 and what is the value of K2. So the temperature of the junction of the two bars means which will become like 315 Kelvin, because here we assumed junction temperature as T0, no. So here we are going to calculate what is the value of T0. So T0, here we got the expression K1 T1 plus K2 T2 by K1 plus K2. See, that is equal to 315 Kelvin in terms of Kelvin, because this value also is in Kelvin and this value is also in Kelvin, and temperature values also they have given in Kelvin. So that we are getting 315 Kelvin. Next, the second one, K dash is equal to, that is what? Equivalent thermal conductivity of the compound bore. 2K1 K2 by K1 plus K2. Right. So K1 is 79 and K2 is 109. You just substitute the values. 2 into 79 into 109 divided by 79 plus 109. 79 plus 109 will give us 91.6 watt per meter per Kelvin. And here also the same thing. I didn't substitute here, but you can, because here we have values, no. See, what is this? 79 into what is T1? 373. So here if you substitute the things, you will get it as 79 into 373 plus 109 into 273 divided by 79 plus 109, which will give us 315 Kelvin. Here K dash will become like 91.6 watt per meter per Kelvin. Next, third one is what? The heat current through the compound bore. It is the second one, it is the third one. The heat current through the compound bore. So what is the heat current? H dash is equal to K dash into A into T1 minus T2 by 2L. So we have to substitute. See, if you substitute the values, you will get it as 91.6 into 0.02 into 373 minus 273. 91.6 into 0.02 into 373 minus 273 divided by 2 into 0.1. 2 into 0.1, which will give us 916.1 watt. Okay, that is. So in this class we discussed two example problems, example 11.6 and example 11.7. In this example 11.6 we calculated temperature of the steel copper junction in the steady state. So which we got it as 44.4 degrees centigrade based on the given data and based on the situation given in the figure. In the next problem, we calculated three things: temperature of the junction of the two bars as shown in the figure, according to the figure, and the equivalent thermal conductivity of the compound bar, and the heat current through the compound bar. So three things we calculated based on the given data. So what is the given data they have given? length of the bar, iron bar, and area of cross section of the iron bar, and length of the brass bar and area of cross section of the brass bar. After that, they have given thermal conductivity of iron and thermal conductivity of brass, and temperature of the free end of the iron as 373 Kelvin and temperature at the free end of the brass as 273 Kelvin. So based on the given data and the situation means figure what they have given in this question, we calculated the three things. First one is the temperature of the junction of the two bars, which we got it as 315 Kelvin. Next, the equivalent thermal conductivity of the compound bar, which we got it as 91.6 watt per meter per Kelvin. The second one is important, right? For NEET point of view or board point of view, this model problem is important. Next, third one, the heat current through the compound bar. The heat current through the compound bar, that we got it as 916.1 watts. Okay, right. So in next class, we will continue with the next continuation topic, that is convection, and after that radiation. Okay, thank you.